We use caches every day, browser cache, Redis, CDNs, but do you know how an LRU cache works under the hood? Today we'll build a production-grade LRU cache with hit/miss tracking, eviction statistics, and access history. It's implemented entirely in one Java class, and we'll walk through it line by line. We start with a generic interface called cache operations. It declares the core contract any cache should have: put to add entries, get to retrieve them, remove, clear, size, contains key, and display stats. The K and V parameters make it type safe. We'll later create caches that hold e.g. string keys and integer values. This interface will be implemented by our LRU cache. LRU cache implements the interface we just defined. It stores a fixed capacity, the maximum number of entries allowed. The actual cache is a LinkedHashMap, which we'll configure shortly to keep entries in access order. 3 counters, hits, misses, evictions, track performance. Access history is a separate map that stores extra metadata, like last access time and how many times a key was accessed, wrapped in an access record object, which we haven't defined yet. It's coming next. Now we see the access record inner class, a small data holder. It records the stored value, the timestamp of the most recent access, and how many times the entry has been accessed. The constructor sets the value, records the current time, and initializes the access count to 1. This is used solely by access history to provide the extra analytics we saw earlier. The constructor takes a capacity and rejects non-positive values. We initialize access history as a plain hash map. The real magic is the linked hash map. We construct it with 3 arguments: initial capacity, a load factor of 0.75, and true. That Boolean means access order instead of insertion order, so every time we get an entry, it moves to the front of the iteration order. We then override remove eldest entry. This method is called automatically after each put. Put first rejects null values to keep the cache clean. Then it inserts the key/value into the underlying linked hash map. If the key already exists, the old value is replaced. Either way the key moves to the most recently used position, because access order is true. We also put a fresh access record into access history. This resets the access count and timestamp each time put is called for a key, which is correct because a new put is like a fresh insertion. Get first checks if the key is present. If yes, it increments hits, retrieves the value, which also moves the entry to the front of the access order in the linked hash map, and updates the access record, sets last access to now and bumps the access count. If the key is missing, we increment misses and return null. This simple method maintains all our stats automatically. Remove deletes a specific key from both the cache and the access history, only if it exists. Clear wipes everything, cache, history, and resets all counters to 0. These operations are straightforward but essential for maintenance. We add convenience methods, size and contains key delegate to the underlying map. GetHitRatio computes the hit percentage, returning 0 if there have been no requests to avoid division by 0. The remaining getters expose the internal counters and capacity. They're used later by the display methods. DisplayStats prints a formatted summary block using the counters we've been maintaining. It shows capacity, current size, hits, misses, total requests, hit ratio percentage, and evictions. The equals.repeat 60 line creates a neat header/footer. This is a user-friendly way to inspect cache health. DisplayCache prints the current cache entries in access order, most recent first, because the linked hash map iterates that way. For each key it shows the value and the access count from the corresponding access record. Display detailed history prints every key ever seen, even evicted ones may still be in access history unless removed, along with its last access timestamp and total accesses. These methods are purely for debugging and demonstration. Now the demonstration begins. We create a cache with capacity 4. We insert 4 entries with string keys and integer values. Then we call DisplayCache to show the current state. The cache is now full. We access user_002 twice, which should increase its access count and move it to the front of the LRU order. Display cache will confirm that. Then we try two non-existent keys, these are cache misses. Display stats shows the hit/miss numbers so far. Adding user_005 exceeds capacity, so the eldest entry, likely user_001 because it hasn't been accessed, is evicted. Display cache will show the new composition. Then we access three keys, these hits adjust the LRU order further. Now we add user_006, again over capacity, so the next least recently used entry, probably user_002, is evicted. Then we try to get the two evicted keys, both return null and count as misses. This showcases cache semantics. We access user_003 times in a row, its access count will jump accordingly. Then we manually remove user_005. Display cache reflects the removal. After removal there's room for another entry. We add user_007, then call display stats and display detailed history to see the final state. Finally we print a couple of custom performance metrics. The output shows hit ratio, total operations, and evictions relative to total accesses. The program compiles and runs cleanly. You'll see the cache state evolve step by step, proving the LRU eviction policy works, the access counters update, and the statistics are accurate. We've built a feature-rich LRU cache from scratch, including performance monitoring and detailed access history. The core mechanic is a LinkedHashMap with access order and a simple override. With this foundation, you can add TTL expiration, persistence, or even a custom replacement policy.